Perfect. Hello. Exciting. So today, thanks everyone for coming. Today we're going to talk about inverse graphics for the first time, actually. Is it just me or is the microphone way louder than usual? Anyways, so what did we talk about last time? Last time we talked about light transport and, I should say up until now, one big topic has been light transport. So how does light bounce around in scenes? We have talked about 3D representations and we had talked about camera models. So basically every part of this image, which is obviously very abstract, but every part of this image we now kind of understand. So last time in particular we talked about light transport. So given light sources in the scene and 3D surfaces and their materials, how do we calculate how light bounces around the scene? And the key thing that we talked about, so we talked about the function signature of rendering. Rendering is just a function that takes as input a 3D scene representation plus a ray parameterization, and then it tells you what color is observed by the ray. And we formalize the color of rays as radiance. Radiance being the fundamental quantity of light, which basically means that radiance is the density of photons at a point in a particular direction at a given wavelength. So actually, that's the spectral radiance. For a given wavelength at a particular point in time, the density of photons in a particular direction. And the unit is energy per time, per unit area, per unit solid angle, per wavelength. So it's all, okay, time makes sense. Unit area also makes sense. So it's right, it's like an infinitesimal point, so like the density of photons traveling through an infinitesimally small point. Per unit solid angle, solid angle is basically I realized we didn't talk about this last time. Do people know what solid angle means? So, good, should have explained it. Solid angle is, imagine you take a point, you draw a sphere around it, and solid angle is basically the surface of the sphere. Like it's basically like you take a cone from the center that originates at the center of the sphere, and the surface of the cone on the surface of the sphere is basically so it's kind of like you're kind of integrating over a field of view is like the way to think about it. So that's what it means. Okay, and then we talked about the rendering equation, and last time I got very confused, if you still remember correctly. So we saw rendering equation is basically telling you how light bounces around in the scene. So we said radiance is the fundamental unit of light. So L is exactly the radiance at a point x in an outgoing direction omega 0. So here is in point x, the outgoing direction. That's, for instance, the direction that my eye is looking from. It's the outgoing direction for a particular wavelength. The radiance of that point in that direction is the radiance that is emitted by that point. Like if you have a lamp, like a light that is emitting photons, right? That makes sense. And then the second part is basically the part of light that is bouncing around in the scene. So that's the light that is reflected from a light that is bouncing around in the scene. So outgoing radiance, emitted radiance, incoming radiance. Then we talked about the BRDF, right? That was this function f. Does it come up here? So the BRDF was this function that tells you for a given incoming and outgoing direction, which fraction of that light is actually being reflected by the surface. And then there was this point about the angle weight of photon density, and I got confused about this last time, but it's actually, of course, it's straightforward. All of this is actually, if you think about the definition of radiance, it makes perfect sense. We said the radiance is per unit area. So like you pick a unit of area and the radiance is the density of photons flowing through that unit of area. And now it just so happens that the second point tells you of all the light that is hitting a surface point, of all of the light that is entering a point on the surface, which fraction of that is reflected, right? And now the point is that if you have a light source, and the light source is, like, imagine you have a flashlight and you shine the light straight onto the surface and it's exactly orthogonal, then you know that the density of photons on the surface will be higher than if you take your light at an angle, right? Because if you take your light at an angle, then this will all be dimmer, versus if you make it a spot, then it's like a spot. And so it then makes sense that basically the density of photons that is reflected by the surface has to be a function of the density of photons that enters the surface at that point. And that's why if you have the lamp at an angle, then the density of photons at on the surface is going to be lower than if you have the light orthogonally to the surface direction. So that makes perfect sense. Last time I got confused about essentially the units. Does that make sense so far? Rendering equation recap. So okay, we just discussed this, great. Cool, so then today we're going to talk about inverse graphics, finally. So this is really exciting. So what is the motivation for inverse graphics, or for, today we're going to talk about differentiable rendering. So what is the motivation for differentiable rendering? Last time we talked about the forward model, which basically, when we say forward model, we usually mean we have, like, in this case, we have the 3D scene, we have light sources, and we go from it's like the operator that takes you from the 3D scene plus the light sources to the image that you observe. Now we want to solve the inverse problem. That's the name of the whole lecture, inverse graphics. We want to go from images to 3D scenes. And the key tool that has been developed for this purpose over the past, I should say, 6 years, so it's a very recent development in our computer vision community, is differentiable rendering. And the key idea of differentiable rendering, you can probably already imagine. The key idea is we're going to take this rendering operator that we discussed last time that takes you from a parameterization of the 3D scene to images, and we're going to make it differentiable. And what that, of course, means is now you can make images part of your loss function. Like any loss you might have, you can make the images that you render of the 3D scene part of your loss function, and then you can solve optimization problems that have as part of the optimization problem the rendering operator. So what does that mean? This is what this then looks like. So what this is usually used for is 3D reconstruction. So in this case here, this is a differentiable renderer in action. In this case, we initialize a 3D scene as a sphere, and now we will have lots of images of a chair. We have access to lots of images and the camera poses of this chair. And now using the differentiable renderer, we can optimize the 3D scene such that every rendering of the 3D scene matches the rendering that we have of the chair, and so we can reconstruct the chair just from the images. And the thing that you see here on the right, at the end of this lecture, you will hopefully understand how this works. The thing that you see here on the right is also a 3D scene that is reconstructed via differentiable rendering. Okay, so recap in figures. So rendering is 3D scene, give me a 3D scene, give me camera poses, and then the renderer gives you for each of the camera poses the image, right? That's the forward model. The inverse model is give me the images, and from the images reconstruct the 3D scene and the camera poses. Makes sense. So this is the inverse. And now this is something we already talked about in the first and second and third lectures. What is the trick, or what's the thing with camera poses? We already know how to get camera poses, right? Does someone remember what I told you in the third lecture? It's like, if you need to get camera poses from a video, what do? You stick it in CallMap. So that's exactly what we actually do. In practice, the camera poses today are still obtained with CallMap. So this is exactly, or like bundle adjustment, this is exactly the tool that we have been using for the past 20 years. This is, I think, about to change in the next year. So if you visit this lecture in a year, it's going to look different. But for now, basically just assume I give you lots of images, and we want to solve the inverse problem. It's true, we want to go from images to the 3D scene and the camera poses, but we're going to factorize it into two problems. The first problem we already know how to solve, which is getting the camera poses from the images, and we're going to run CallMap to do that, or basically we're going to use classic bundle adjustment. Okay, so you stick it into CallMap, you get the camera poses, which is basically solving this optimization problem, as you might remember. And then the problem simplifies. The problem of inverse graphics, the way it's been treated over this past 6 years, then simplifies to, given the images and the camera poses, reconstruct the 3D scene. So this is the problem that we're going to discuss how we can solve it in today's lecture. Make sense? Great. Exciting. So the starting point is 3D scene representations. So this we already talked about in the 2 lectures ago, right? Or actually, we had 2 lectures that talk about how can you parameterize 3D scenes. So the first step is we want to reconstruct 3D scenes. We first need to find some parameterization of a 3D scene. And there's like some modeling choices to make here, but fundamentally you already know how to do this. You have to parameterize a function in 3D. You can parameterize it as a voxel grid, right? You can parameterize it as a neural field. If you had any questions on these topics, now would be a good time to ask them. Just as a reminder, these functions allow you, basically, you have a function that is defined in 3D space, which means you give it a 3D coordinate, it tells you what is at that 3D coordinate, and you can parameterize that in many different ways, right? Okay, good. So we assume that we understand that by now. And then differentiable rendering can basically be posed like this. We're going levels of abstraction down. So now we say we have our scene representation, that is, for instance, our voxel grid. on that voxel grid, we're now going to define a differentiable renderer that takes as input the voxel grid plus the camera poses, right? And now what the renderer is going to do is it's going to render images, and then we compare those to the ground truth images that we captured, and then we're going to take the derivative of the loss with respect to the 3D scene representation, like literally AutoGrad, right? In practice, you're going to implement this yourself in the homework. In practice, you're going to implement the renderer in PyTorch. Like literally you go and you're going to implement the algorithm that we discussed today in PyTorch. And then once you have it, you're going to give it a voxel grid. You're going to feed the voxel grid as input to your differential renderer as well as some camera poses. For each of the camera poses, your differential renderer written in PyTorch will give you an image. You compare that to the image, have an L2 loss, like a reconstruction loss, and then you just say minimize this loss. And then it's going to GPU go brr, and then after at the end, you get a voxel grid out that parameterizes the 3D scene, right? Okay, so one more thing to note is, of course, in the beginning, I was lazy here. In the beginning, of course, these will make no sense, right? These images, you don't know the scene up front, so you're going to randomly initialize your voxel grid. Could be like just empty, or you just add like a little bit of noise or something. So in the beginning, the images won't make any sense, of course. Questions? Yes?
We now chose like a voxel grid as a scene representation.
Yeah.
I assume like that is much easier than choosing, for example, another scene representation, for example, just having meshes that do like differentiable renders directly on meshes also.
Great question. This is something we'll talk about today. And in the next lecture. So basically, it's interesting. So last time I gave this lecture, the status was that all the differentiable renderers that actually worked used volumetric representations of fields. So all of them were parameterizations of fields. So either they were voxel grids, or they were neural fields, which basically like neural networks, right? Or they were representations that mixed discrete and neural representations, which we also talked about, right? We hopefully remember we had a voxel grid, for instance. We can store features in the voxel grid, take a point, interpolate the features, stick that into a neural network, and then use it to interpolate the features in the voxel grid. So these hybrid representations. That is the only differentiable rendering that actually worked 1 year ago. But status 1 month ago, there is a new way of doing it, which is called 3D Gaussian splatting, which some of you might have seen. We are going to talk about that. I have to make those. That's a new lecture. I haven't made it yet. I'm going to talk about that in the next lecture. Two things are true. One, the things that we're learning today are also necessary to understand what is going on there. But then the second thing is that in fact, shuffles up this picture a little bit, because now there are alternative representations that allow you to do this. But meshes are not one of them. So long story short, with meshes, it really still doesn't work, and it's probably not going to work. Well, I shouldn't say it. There are some algorithms that do it with meshes, but they all work much, much worse than the ones that. So yeah, the choice of representation is important, and actually, I'll just forego this discussion until the end, and then it'll make much more sense. Any other questions? But great question, yes, as you can tell from the lengthy answer. Any other questions? Great. Then let's jump right in. Okay, and like I also just want to introduce some nomenclature or some terminology. So maybe you know this like observable versus latent variables. What are the latent variables? Means usually like these are parameters of your of the thing that you're trying to solve for that you don't directly observe. So you have the observable variables in this case. What are those? These are the pixel colors. And the latent variables, you could call the geometry, the 3D geometry and the 3D appearance. So you don't directly, you have to solve for the 3D geometry and the appearance. These we would call latents. Right? Great. No questions. Okay, so here's how we're first going to talk about, in this lecture, we're going to talk about differentiable renderers for fields. So for volumetric representations, like voxel grids, like neural fields and stuff like that. All of them work basically the same way. Let's imagine you had a 3D representation, like in this case, it's a neural field, which means you give it a 3D, it's a neural network, you give it a 3D coordinate, it gives you something back. Or it could be a voxel grid, same thing, right? You give it a 3D coordinate, it gives you something back. Okay, so let's say we had a representation like that. And now, what does rendering mean? We have a ray, and that ray is going to shoot into our volume. In this case, I have put a bunny here, but of course, initially, we don't know that there's a bunny here. but just for visualization, imagine, for instance, this were a voxel grid, right? So we're going to shoot our ray into the volume, and now we want to render the volume from this ray. We want to get the color of this ray, right? Okay, all of these algorithms basically work the same way. They work by taking this ray and sampling points along this ray. And why is that? The thing that you have to imagine is that, and we discussed this before, in all of these volumetric representations, there's always a notion of having to find the surface, because the thing that the representation doesn't give you is it doesn't immediately give you the surface. If you had a mesh or a point cloud, then you would know where the surface is by virtue of knowing that every vertex lies on the surface or every point lies on the surface. But for 3D volumetric representations, a priori, you don't know where the surface lies. And of course, yeah. Great question. CalMap, that is a great question. So the point that Cairo is raising is that he's saying, well, but we had to run structure for motion, and structure for motion, doesn't structure for motion already solve for the camera poses as well as the coordinates of some 3D points, right? And the answer is yes, it does. There's a few catches. The first catch is that you usually only get sparse point clouds from CalMap. So when you run CalMap, the thing that you get is you get basically the 3D coordinates of some key points in each image. So for each image, you'll have some key points, and now you know the geometry of these key points. Now you can run this multi-view stereo algorithm on top of that, which then reconstructs dense point clouds, and these have better geometry, so then you get dense depth maps. And now, it is indeed true that you can use these, and I'm not sure if, I don't have that in my slides right now, but there are methods that say, okay, we already have to run this, why don't we use these as initialization or something like that? So you can do that. The problem is that these point clouds, turns out, aren't actually that precise. So it turns out that one good way of thinking about all of this differentiable rendering stuff, at least in this framework in which we're talking about it today, is it is status today the most precise way of doing 3D reconstruction. Nothing else comes close, other than maybe taking, like, I don't know, I've never done that, but maybe like a laser scanner or something, where you have like and you just take like a super great amount of time of like spinning something on a little turntable and scanning it with like a super complicated 3D scanner. But other than that, the best we can do today, by far, of doing 3D reconstruction is by the methods we're discussing today. So long story short, yes, CalMap solves for depth maps, but they're not that precise, and they're also not dense enough. And it turns out we can actually solve for more with these things. But good question. Other questions? Great. So what all of these methods basically do is the first step will be that they basically have to sample lots of points along each ray. And why is that? It's because a priori you don't know where the surface lies. So if you knew where the surface would lie, you would basically know that the only color you have to worry about is wherever the surface, but you don't know where the surface lies yet. And so all of these algorithms that we're going to talk about will basically start by having a notion of sampling lots of points along a ray. And then there's going to be a notion of integrating the information of these samples along the ray. So you're going to sample lots of points, and then you're going to take a piece of information from each of these points, and you're going to say, okay, the final color of the ray is going to be a function of all of these samples along the ray. And now this relates to your question that you asked earlier. You asked why, can't we use meshes for reconstruction? Let's actually talk about that now, because it's a good question. So, so let's say we wanted to optimize a mesh according to like some images, right? So let's imagine you initialized a sphere, for instance. So you say, okay, you want to match the chair that we just saw earlier, and now we initialize a sphere that is floating in space, and we're going to render the sphere from many angles, and then we compare these renderings against the ground truth images. The problem that you run into in this case is one of local minima. So why is it hard to optimize a mesh? Why is it hard to solve the differential rendering problems with meshes? It's in a roundabout way, it's actually exactly because you're not taking lots of points along each ray, but instead when you render a mesh, you always only consider one estimate of the depth along each ray. And you're basically saying, here's the surface. Okay, and now what has to happen is you have to locally move the surface around. Like that's what you would do if you were to differentially optimize mesh. And it turns out that's the thing that is really hard. So that's the thing you basically can't really do, because if you try to just take a single estimate of the surface and wiggle that surface estimate around, you'll end up in lots of local minima. And these local minima relate to the local minimum that we discussed before when we talked about the multi-scale thing. Do you remember that? we had this discussion about how you need multi-scale losses. And we discussed how that was like what the problem was. And in differential rendering, you might have a similar problem. Imagine you have like a mesh that is floating here, and now you have two images of the mesh, and now you want to move the vertex to match both of the images. The thing that often happens is that the vertex might get stuck in a local minimum, which basically means at the position where the vertex is right now, it explains a certain aspect of the image. And if you wiggle it around, actually the loss increases. But actually the correct solution would be to move the vertex much further, and that's not happening. And so the algorithms we're talking about today all have this component of like taking lots of samples along array because you a priori don't know where the surface lies. And so what this gives you is it basically gives you better gradients into the geometry. It makes more sense when we discuss it. Okay, so the first algorithm we're going to talk about is the sphere tracing algorithm. And the sphere tracing algorithm, I've briefly mentioned it before, is an algorithm for differentiably rendering signed distance functions. So signed distance functions were one of the different geometry representations we discussed. Let's talk about signed distance functions again. So the signed distance function, let's consider this. Actually, we're just going to talk about this, about the sphere tracing algorithm. So who remember what a signed distance function was? Everyone. Does anyone not remember what a signed distance function was? Okay, you don't remember? Okay, so the signed distance function was the function that maps every point in space to the distance to the closest scene surface. Okay, so let's say we wanted to render our scene here. We're going to place the camera in the scene, and we're going to now we want to render differentiably the scene from this camera's perspective. And the first step we have to do is exactly as we just discussed. We basically have to find the surface. For each of these rays, we'll have to find a differentiable way of finding the surface along the ray. And then we want to get the color at that surface, and then we want to render that color for that ray. So the first question, how do we parameterize the scene geometry? I already gave it away. We're going to do it via a signed distance function. So the signed distance function, if you recall, was this function that maps every point to the distance to the closest scene surface. And in this case, for instance, or like alternatively, you can imagine it's always the radius of the sphere with the largest radius that you could, like, it's the largest sphere you can draw around a point that just barely touches the geometry of the scene. The radius of that is the signed distance at that point. And that's actually where the name sphere tracing comes from, as we'll see in a moment. Okay, and in particular, as a reminder, the signed distance is 0 on the surfaces of the scene. So on every surface of the scene, the signed distance is 0 by definition, because on a surface point, the distance to the closest surface is 0, right? Okay, so here's a differentiable algorithm that we can build So what's the dumbest differentiable algorithm, or like, what's the dumbest algorithm that we could build that would render, that would find the surface along each ray? So remember the signed distance is positive outside of objects, and it's negative inside of objects. So what is the first way you could come up with finding the surface along each ray? Yes? Right. Makes sense, right? That's exactly right. So the first thing you could do is you could say, okay, I have the ray, and now I'm just going to sample points along my ray, maybe at a fixed distance, right? And then for each interval, I'm going to see if the signed distance function changed its sign. This is similar to if you remember, this is kind of similar to what this marching cubes algorithm did to extract the surface from a signed distance function. That works. So we basically have to march along the ray until we find the point where it switches the sign, or equivalently, we have to march along the ray until we find a point where the signed distance is 0 for the first time. And why, for the first time, by the way, we want to find the first intersection with the scene geometry, right? It doesn't serve, like we need to find the first time that the ray intersects the geometry of the scene. So the naive solution is basically constant step length. And that actually works. It's, however, expensive. So there's actually a smarter way of doing it. And maybe someone already knows, or maybe someone can imagine what could be a smart way in which we could exploit the fact that we know the signed distance at every point. Mm-hmm. Mm-hmm. Yeah, binary search is something you can do. Yes?
Once you know the signed distance
That's right. Did you know this already, or did you just come up with this? No, yeah, it's that. Okay, good. That's exactly right, right? So like there is this funny trick with the sign distance, which knows the sign you know that the sign distance means it's the radius of the largest sphere that you can draw around this point without touching the, stepping through the geometry. So what you do is like, basically, imagine, for instance, you had a neural field, right? You had a neural network that parameterizes the 3D scene. Just imagine this was one neural network. What do? You start somewhere on the array close to the camera. You get the x-coordinate of that point. You're going to give it to your neural network. And now your neural network, you have built it such that it outputs a scalar. Right? So it outputs a scalar. And now you say, I call this scalar my sign distance function. I'm going to interpret the scalar as the sign distance of the scene at that point. Okay? And now you're going to take that sign distance value, and you're just going to say, okay, I can advance along this array at least according to that sign distance value. In fact, if it was already the correct sign distance function, right, you would sample your neural network here, it would give you the radius of the sphere, and then you could just advance along the array according to that value that you just predicted, right? Does that make sense? Great. So, and as, what was your name? As Jakob just said, so the thing that happens is that you have a neat little guarantee, which is you're guaranteed to eventually, if you do this infinitely long, you're guaranteed to eventually find the surface, right? Because clearly the step length is never 0 until you're on the surface. So you always have a non-negative, always have a positive step length as long as you're not on the surface. And once you're on the surface, the sign distance would be 0, and then you'd be done. Great. You're also guaranteed, it turns out, to not step through a surface. So you're, for the same reason, right? Because you know that the sign distance is basically the most, so to speak, in the best case, you're exactly orthogonal to the surface, and in that case, the sign distance is exactly the distance to the surface. So then you would get to the surface in one step. You just predict the sign distance, you get to the surface in one step, and you're done. In every other case, it's lower. It's like it's guaranteed to be a upper bound, it's guaranteed to be smaller than the distance to the surface along the ray. Okay, whatever. So we do this a constant number of times. Okay, so how do we make this differentiable? So clearly this algorithm converges to the surface. You can make it differentiable, for instance, by just saying I'm going to do a constant number of steps. So you say, okay, we're going to do 20 steps of this algorithm. So we take a sample, we predict a step length, we advance along the ray, predict a step length, do that 20 times. And then you call the final estimate, along the ray your surface. Okay, and then you can now have found your surface, and now you need to just still predict a color at that surface point. So what are you going to do? You're going to take the coordinate of that 3D point, and you're going to query your scene representation a final time. So for instance, you go into your voxel grid, and you query your voxel grid a final time, and you ask it for color at that point. And then you're going to call the color of that ray, whichever color your scene representation has at that point. So what does that mean? It means that your scene representation is going to have two outputs now. One is going to be a scalar, which you're going to interpret as the sign distance, and the other one is going to be a color that you're going to interpret as the color of the point. And then you're going to use the sign distance values to find the surface, and then once you have found the surface, you ask the representation a final time about the color, and then you get the color at that point, and that's the color you're going to render for that ray. Does that make sense? Concerns? Questions? Good. And the nice thing is everything we just discussed is perfectly differentiable. You don't need to do anything special. The thing that we just discussed is perfectly differentiable, and you can just backpropagate through it. And why is that? So clearly, once you have found the surface, you're just querying a scene representation a single time, and you're asking what's the color at that point. And if that color was incorrect, you just change that color, right? So that part is straightforward. But now, how do you get gradients for the geometry of the scene? So like, why can you optimize the geometry of the scene? Well, you have done a constant number of steps. Each of the steps, what is each of the steps? Each of the steps is basically just taking a 3D coordinate, querying your network for a distance, and then just adding that to your current estimate of the distance along the ray, right? So that's clearly differentiable. There's nothing special in here. And you're doing that a constant number of times, so it's just the chain rule. So you're just going, what's the derivative of the final color with respect to each of the steps? So this is straightforward differentiable, and then you have then you can just optimize it. Any questions? Yes?
Is the rate of convergence fast enough that you go?
Great question. The question. No, this is a concern. This is a great question. So the question is like, what is the rate of convergence on this thing? And the point that, what's your name? Lucas? Are you from Germany, Lucas?
Yep, I mean, kind of, my mom's German.
Ah, interesting. This is a great question. So let's say there's basically, we can, let's say this is our surface, and we're rendering this ray here. What's the convergence rate of sphere tracing on this scene? It's one step, right? Because you're unless there's other surfaces around here, it's exactly one step. You're going to query the scene representation, I don't know, at this point. You're going to get exactly the radius of the sphere. You're going to advance it going here. Done. One step. Very fast. One step is enough. What if the scene looks like this? So now you have a surface that is parallel to the ray, and you have another surface that you're actually trying to find, right? You're trying to find this intersection point. So what's going to be the step length in this case? The step length is going to be always the radius of each of these little spheres here, right? So you're going to advance from here to here, little sphere. So you're going to take lots of steps. Now the question that Lucas is asking is, are we always guaranteed to find the surface in the constant number of steps that we picked? And the answer is no. We are not. And in fact, so this is one of the downsides of sphere tracing. So like there's like, if you, in scenes that, it is indeed not always straightforward to find the correct surface in the number of steps. There are certain ways in which you can allow your network to cheat a little bit, or like to store more information than just the signed distance. So for instance, you can say, give me the, there's like you can imagine that the network also stores a direction-dependent signed distance. So you not only give the network the current 3D coordinate, but you also give it a direction, and you ask it in this direction, how far is the closest surface away? But no, this is totally a concern. And there's another way of optimizing it. You can, in fact, always do the thing that we discussed earlier, where you just discretize steps along the ray and you find the intersection, and you do it with like a search along the ray. That's another way of doing it. And that has another constraint, though, which is that you need to pick your near and far plane up front. So you need to say, where do you place your samples up front? And it turns out that no matter what you do, you have to die one death, basically. So in practice, sphere tracing is fast. And there's also like lots of ways of mixing the two. You can, for instance, imagine discretize it. And then after you discretize it, you do like a few sphere tracing steps that start along each. Anyways, good question. Any other questions? Okay, good. Yeah, and actually, with respect to your question, if you're interested in the sphere tracing algorithm, here's a few other papers you might want to read. There's a few fancy tricks you could do. One fancy trick, for instance, it turns out that the derivative of the position of the final surface, you don't actually need to compute the chain. You don't need to go you don't need to use the chain rule at all to get the final derivative of the point on the surface. So what you're actually interested in the end, right, is you're interested in what's the gradient of my color with respect to the position of the final surface, like with the position of the final estimate, right? And it turns out that you can get the gradient of that position without applying the chain rule to each of the steps. But we're not going to talk about it because it's kind of complicated and it's not that important. But yes? No, because you still have to find the surface. So no matter what you do, you always have to.
But you can get arbitrarily fancy with like variable number of steps or something and still.
Yes. Oh, yeah. This is exactly true. So what the thing that I just mentioned allows. So the thing that I just mentioned is, it turns out that once you have found the surface, it turns out that to compute the gradient of the position of the surface with respect to the parameters, with respect to the signed distance function, basically, or with respect to the parameters in your voxel grid equivalently, it turns out you don't actually need to do the chain rule. What that means exactly is that you can uncouple the two steps. You can decouple the step of finding the surface. You can use anything you want for finding the surface, any non-differentiable fancy binary search, whatever you want. the moment you have found the surface, the gradient is closed form, with some caveats again. The key caveat being actually that if you don't find the surface, then you don't know what the gradient is. Anyways, if you're interested in this, come to my office hour, and I'm happy to go into any amount of detail. But now let's go to the currently most popular way of doing differential rendering, which is called volumetric rendering. And this is now, yeah, this is going to be great. So volumetric rendering. Still, so first of all, like, let me briefly refresh. It makes sense why, right, we said we take samples along each ray, and that's how we, like, this is, it now makes sense, like, in sphere tracing, right, the samples along this ray are the samples where you sample this, is what you do to find the surface. In volume rendering, it's going to be something slightly different, but it's going to still do the same thing. Okay, so volume rendering is actually something that doesn't have anything to do with differential rendering at all. It is actually just it is again like a physics-informed way of doing light transport. So in a way, we could even have discussed it in the previous lecture, but it turns out that before differential rendering, people didn't use volume rendering as much. You have seen volume rendering before if you watch movies where there's smoke or something like that in the movie that is CGI and generated, then the way that that smoke is rendered is using volume rendering. And in a moment, you'll see why. But it turns out that volume rendering is extremely useful for differentiable rendering. Okay, so what is the idea of volume rendering? In volume rendering, you don't model the geometry of the scene as a sign distance function. Instead, you model the geometry of the scene via the density at every point. And when we say density, we mean basically how much light. The opacity is actually a better way of saying it. So at every point, you have a representation of how opaque the scene is at that point. So in a way, what you're doing is you're modeling the scene as a cloud of tiny colored particles. So imagine like a cloud. A cloud is like a smoke. Smoke is millions or like billions of tiny particles. And then what you're going to say is we're going to have a camera. The camera shoots a ray. The ray has, I hope you still remember how to compute the ray. And so now we're going to do some physics modeling. We're going to say if a ray is traveling through the scene and it hits a particle at a depth t, so t is the distance that you have traveled along the ray, then you're going to return, then the rendering algorithm will return the color at that location, the color of that particle. So you shoot a ray, the light ray hits the particle, and if it hits the particle, then you're going to return the color of the particle. Does that make sense? And now, how do you make it? How to make it soft? You make it soft by saying that you're going to do probabilistic modeling. You're going to say we're going to model with opacity. We're going to model the probability that at this point the ray is going to hit a particle. So at every point in space, you're going to say our scene representation stores the probability that if a light ray goes through that point in space, it's going to end at that point in space. It's going to hit a surface at that point. So that's kind of a soft way of parametrizing surfaces, right? Like the surface has a certain density. And that is exactly known as the volume density. And hence the name volume rendering. Okay, so just as a record, for the record, that already tells you what your voxel grid is storing. Your voxel grid is storing in every, or like your whatever scene representation you so choose. Your scene representation at every point will give you a density and a color. Is the density being the probability that a ray that goes to that point will stop at that point, and the color would be the color that if a ray stopped at that point, that would be the color of the ray. Okay, so now how do we build a rendering algorithm around this model of the scene? We're going to basically shift around these probabilities a little bit. So first thing we're going to write down is the transmittance, and the transmittance is the probability that a light ray that this light ray doesn't hit any particle up until this position t. So t, transmittance of this depth t, is the probability that we don't hit any other particle before t. And it maybe makes sense why we're interested in this. Because we're interested in, well, actually, it's going to be easy to explain in a moment. Okay, so we have the probability that the light ray doesn't hit any particle up until this point, and then we have the probability that we will hit a particle at that point, given as this density that we have discussed. Okay, so if we write it down, so the probability that we don't have a hit up until t, and that we will hit a particle at this position, at like this infinitesimal neighborhood around t, is the probability that we don't hit a particle until t times the probability, which is 1 minus the probability that we will hit a particle at this position. And yeah, I should say the dt is because we're like interested in an infinitesimal neighborhood in an infinitesimal neighborhood around this depth t. Make sense so far? Okay, good. Yes, question. Yeah, it is fair because like we introduced it as the probability, right? So yeah, it's fair. I'm not sure if the p's should be necessarily there. Yeah, so because we just said that it's like I think it's so yeah. I should also say these slides are from Ben. I think the reason why Ben put this here is because he wanted to make the point about the probability explicit. So he wanted to say, like, right now we're talking about the probabilities that are involved in this. But you are actually right that the t, we introduced it as the probability, so you wouldn't have to. And in fact, we're going to drop these now. So in fact, here's what we're going to do now. We're going to drop the p's, and we're just going to say, okay, so the transmittance, so the probability that we don't hit a particle up until t, and then in this infinitesimal extra step, which is like the size of this additional particle at this point t, is this infinitesimal dt, is going to be the transmittance up until t times 1 minus the probability that we are being like reflected at that particle, which is like the sigma t. Does that make sense? Okay, and now basically we're not going to talk about this. If you're interested in this, you can read this volume rendering digest from Andrea Tagliasacchi and Ben Bildenhall, which goes into detail. But basically what you're going to now do is you're going to just solve this little differential equation. It's a very simple differential equation. You can just solve it via integration. But what we're going to do is we're going to solve it for the transmittance. Because here we have a differential equation that describes the transmittance implicitly. We want to solve for the transmittance. We're just going to hit it with a stick and integrate it until the transmittance finds out. And it turns out you can just solve this little equation. And if you solve it via integration, you get out this thing. You get out the transmittance, so the probability that the light ray isn't reflected or like doesn't hit a particle between A and B. So like you shoot the ray and then you pick a boundary A and B. And the probability that the light ray isn't hitting a particle between A and B is exactly this term here. So this is just solving this little differential equation. It turns out it's this exponential of the negative of the integral of the density. And now, okay, so forget the math for a moment. Intuitively makes sense, right? You're basically saying, what's the probability that you're not hitting a particle? It's going to be inversely proportional to how opaque how dense your volume is, right? If it's really dense, then there's a zero chance. Like if you're looking at the probability that you haven't hit a particle until on this way until t here, the probability is 0 because there's something in between that has really, really high density, right? So lots of math, but the intuition is clear. So in many ways, you could have even come up with this, and actually, you don't need this physics-based interpretation to come up with something like this, as you're going to see in the end. It turns out if you would have just thought about how could I build a renderer that like does it like this, you could come up with this. In fact, I did come up with something similar to this, which doesn't work as well in 2018, without knowing any of this stuff, which it would have been way better if I had known about the stuff, which is known since the 70s, but I didn't. So, but it turns out you don't need to know this to build something that works. But it is very helpful to know about it. Okay, so now you know this. The next thing you could say is, well, in particular, we're going to define, so this is the start point, we're going to define the transmittance up until this point t along the ray as the probability that from z to t we don't hit anything. So we just like change the things. So the probability that there are no hits until this depth t is equal to this thing. Great. And now why did we do all of this? The reason why we did all of this is very, very cool, which is that now you can say that 1 minus this thing is the cumulative distribution function. So it's basically, it tells you for every point along the ray, what is the probability that we have gotten so far, basically, right? That's exactly what the transmittance tells you. And the cool thing now is that the probability that the ray stops exactly at t is this. So it's the probability that you haven't stopped until the transmittance until t times the density at this point. And now it turns out that you can use this as to have a probabilistic expression for the color of the ray. Because now what you're going to do is you're going to say, okay, I have my volume. You remember we have modeled our scene as this cloud of particles. Every particle has a density and every particle has a color. And now we can say if I shoot a ray, the color of this ray is the expected value of the probability that the ray stops at any point along the ray times the color at that position. So we're basically expressing the color of the ray as a weighted sum of all the colors along the ray, weighted by the probability that the ray got until there. Does that make sense? And now the thing that I want you to appreciate for a moment is that this is the reason, this was kind of the key reason that made differentiable rendering work really well. If you think about the gradients that you get from that, so because every point along the ray is involved in the color of the ray, like because every point along the ray is involved in making the color of that ray, you get a very nice gradient for every point along the ray. So this is really nice for optimization. You're sampling all these points. You don't know where the surface is up front, but each of the points along the ray contributes to the color of that ray. In other words, the gradient of the color of the ray with respect to each point along the ray is not zero, unless you initialize it really badly, which in turn means that this is really nice for gradient-based optimization. And this is now the difference to like mesh-based optimization, where in mesh-based optimization you have one surface, and if this, imagine you initialize the surface here, but the true surface is like somewhere here. Now this surface would have to move all the way to here in order for your loss to be low, while in this case you just have to increase the density of this point, and then you're good. So you don't have to move anything, you're just shifting densities around. Does that make sense intuitively? Great. Okay, but we're actually not there. I skipped ahead a little bit. So this is just the intuition now. The color of the ray is now computed as an expected value, which is the transmittance, the probability that we haven't hit anything up until this point, times the probability that we will hit something at this point, which is exactly the density, times the color at that point. And now, how do you actually implement this, which is what you're going to do with some help. It turns out this is an integral. We can approximate this integral via a quadrature. Quadrature just means we take discrete samples along the ray. So we're going to just pick discrete samples along the ray. And in particular, the way you usually do this is you define a near plane, you define a far plane. You say, I assume that my whole scene is contained between those two planes. And this is a hyperparameter. You're assuming this. You're saying, okay, I assume nothing is in front of my camera like 20 centimeters. That's where I start sampling, and I stop sampling like, I don't know, 10 meters away. And then you discretize the space. And then you say the integral along the ray, I'm going to approximate it via the samples that I take along the ray. So now we have split our ray into these n+1 segments. Is it n? Yeah, n+1 segments. And now how can we approximate the integral? Yeah, we're going to talk about this. The first thing, what we're basically doing is we're going to assume that the density and the color are constant in each of these segments. So this is an assumption we're going to make. So we're saying we're taking our ray, we're discretizing it, we're going to assume that the density and color are approximately constant along each segment. Yes?
Just a question about the near and far plane.
Yeah.
If you have like a real world scene, I mean, like, I guess you could just pick them arbitrarily, but you don't have any like sense from your data of depth, right?
Did everyone catch the question? It's a good question. So the question was like, in the real world, you don't know your scene up front. So if you don't know your scene up front, how do you know how to pick the near and far plane? That is a good question indeed. Cairo, since you asked the other question before, can you imagine one way of doing it? This is a...
Well, if you define it as time distance function, with the first surfaces, possibly find the last surfaces.
Right. A good point. In practice, what you do is you use COMAP. So you reconstruct. So because previously you asked this good question, right? Okay, we already solved for the approximate geometry. And it turns out this is one of the uses. So you don't have good geometry for every point, but you have the approximate depth map, like you have sparse depth maps for everything. So you can use those to set your near and far planes. Or alternatively, you just try. And there is something insidious here. It's like, these are very annoying things. Like David has to struggle with this as we speak. So he's working on this right now. So here's something really annoying. When you reconstruct scenes with COMAP, then the scale of the scene is arbitrary. We talked about this once before. You can always scale, that you can basically take all the points, scale them by a scalar, and then you also just scale the camera poses at the same time. And all of these solutions are valid from the perspective of COMAP. And COMAP will give you a random one. You can't You can't reasonably fix the scale up one. So what that means is if you reconstruct 1,000 scenes, each one of them will have a different scale, which means technically your near and far plane has to be different for each of your 1,000 scales, for each of your 1,000 scenes. Even if the scenes are like indoor rooms, and then in an indoor room you can say, oh, like my near and far plane are going to be 10 centimeters and 10 meters. For every indoor scene, that's good enough. But the problem is you don't know what 10 centimeters is because COMAP doesn't give you a metric reconstruction of your scene. So you're screwed. It's really annoying, actually. Yeah. Okay, good. Okay, so basically, we're just going to go through this. Okay, I'm going to ask you, what's the appetite for actually hearing about this volume rendering integral in more detail? Like, do you want to know how to solve it, or do you want to just skip to the fun part where you see pretty images? Okay, go through the integral. Okay, he said so. No, I mean, I think it's good. It's a good exercise, right? Okay, so but so far everything makes sense, right? So like we're expressing the color of the ray as the expected value of that all makes sense, right? Okay, good. So now how are we actually going to compute the integral? We're going to take samples along the ray. We're going to assume that the color and the density of each of the segments are constant. So basically now what that allows us to do is it allows us to express this integral as a sum of piecewise integrals. We're basically going to say we have a sum we have n segments. We're going to take the color of the ray is now a sum of n pieces, and for each of the pieces, the color in that piece is going to be given like this. So now the density and the color are not continuous anymore. They're now indexed by the segment because they're constant in each of the segments. And now the reason why this still is so complicated, why isn't this just now straightforwardly a sum? The reason is because we can totally assume that the density and the color are constant in each of the segments, but the transmittance, the probability that the ray stops, is definitely not constant in each of these segments. And you can see why that is true, even though the density is constant along the ray. Depending on the density, the transmittance is clearly at least a linear function. Oh, it is, in fact, a linear function, right? If the density is like any scalar, then basically the transmittance drops off with a linear factor as you go along the segment, right? Does that make sense? Good, okay. And so we have to account for that. We have to account for the fact that in each of the segments, the transmittance is actually varying. And it's actually not that complicated. We're just going to plug and play from what we had before. So this is the thing that we derived before. We said the transmittance, so the probability that you're not hitting anything up until the point t is proportional to the exponential of the negative integral of the volume densities until that point. This is intuitively all the thing that we just discussed before. And yeah, sorry, I messed up. So we're going to split this transmittant t. We can basically pick an arbitrary point in between, and we say the transmittance is the product of these two things. And since that is true, the first part, right? I wish I would have. It's easier to explain it, I think, in this figure actually. So in this figure, it's easier to explain. So imagine we're like in this segment right now. So the transmittance can be split into two pieces. One is the transmittance of this whole block, and that transmittance is constant, right? Like no matter where you are in this segment, the transmittance of this block always stays constant because you already integrated over that part. So this transmittance is a constant. And then this transmittance is only varying as you're moving through this thing. And this is why we can split the transmittance at a point. We can split the transmittance at a point t into two parts. One is the integral over all previous segments, and then the second part is the integral only throughout part of the segment that we're currently in. So this is the split. And then it turns out this one is really just a sum of constant transmittance, right? Like it's always like you. This stays constant as you're computing this integral. And then the second part is the only part that we have to actually integrate. But here it's not that complicated, right? It's just linear with the distance, right? So if the density is constant in the segment, so the transmittance is just going to linearly drop off as you're going through the segment. Nodding heads. Everyone makes sense? Yes?
Why do you have the box?
Closed form, you mean?
Yeah.
It's unfortunately very much not closed form. Yeah, actually, it's a great question for sure. So So the question is, like, why do we have to approximate this integral? Can't you just compute it closed form? And actually, it's a very good question, because for certain geometries, you could compute it closed form. I don't know for which, actually. You're welcome to try out. But I could, for instance, imagine if you had a very simple geometry, like you have a plane that is floating in space, and you're rendering an array that is orthogonal to the plane, then I could imagine maybe this integral might be closed form, because then the density along the ray is maybe just a Dirac pulse, and then the integral is straightforward. But now imagine you have some really complicated geometry. Like, you can't even give me the equation that parameterizes the surface in 3D. So, like, the integral is definitely not closed form in this case. Another way of seeing it is that you're trying to solve for the geometry, right? So you don't know the geometry up front. You're trying to solve for a voxel grid where every voxel stores the density at that position in space. And so you, unfortunately, no, the integral is not closed form. Yes? This is a great question. So Kyra is asking the question, wouldn't we have to integrate the network? Because let's say, for instance, the way we parameterize the density is via a neural network, right? So we have a neural network that takes a 3D coordinate as input, and it gives you the density at that 3D coordinate. That would be one way we could parameterize this field. Does that make sense? Okay, so let's say we did that. Then let me just hook on to one thing, because this is something I actually tried to figure out for some time. Then in theory, wouldn't it be cool if you could just integrate over the neural network directly? Like the neural, like, let me clarify what I mean. Imagine I gave you a function f of x, and f maps from R3, which is like a 3D coordinate, to just the density. So the density is just a scalar value. So now you're trying to compute this integral here, right? So just to be clear, this density here is now the output of a neural network, and you're trying to output your integral. Okay. So wouldn't it be neat if you could compute something like this? Like, right? Wouldn't it be neat if you could just directly integrate the neural network? Like, and I think we discussed this briefly before. Unfortunately, neural networks are very much not analytically integratable. And this relates to the question that you just asked, like, why can't we just compute the integral analytically? Just think about what the shape of this function is. Like, don't get me wrong, not at all obvious. Many people tried. But the shape of this neural network is really like its value of like A times value of B. I don't know. This is a two-layer neural network, let's say, plus, I don't know, B plus A dx. So it's just a nested value times affine, right? And this thing has absolutely no closed form integral. And I tried, and many other people tried, finding neural network architectures that have closed form integrals. No one has found a way of doing that yet, unfortunately. Would be really neat. Does that make sense? Good question. Make sense? Cool. Great. And so now it turns out, now we can actually just, I'm going to skip, well, actually we can talk about it. Now you can just drop the thing that we just solved for in. So you can take this, you drop the expression for t that we just derived in. So one part of t is just the previous segments, and those you don't have to integrate, because for the purpose of the current segment, these are constant. So the transmittance of all the previous segments is constant. And then the only thing you actually do have to integrate is the transmittance throughout the current segment. And this is just this tiny expression here. And then you can just like reshuffle, and you can just reshuffle it, and this pops out. So now you have an expression for the expected value, like the color as the expected value of the color along the ray, weighted by the densities along the ray. Okay, long story short, and this is now exactly what you would literally code up. So if you code it, you can now, you will actually code this up in your homework. And it really isn't actually that hard. So just in summary, you have this ray. The color along this ray is going to be a sum of, is going to be a weighted sum of colors. So you're going to take the ray, you're going to discretize it into points along the ray. For each of the points, you're going to get a color, and for each of the points, you're going to get a density. And now you're going to express the color of the ray as a weighted sum of the colors of the samples, weighted by a term that you will compute, and the term is going to be the thing that we just derived for the transmittance. This is just a different way of writing the integral, but the I realize now it would be better, like for the next lecture, I'm going to just pop this everything in there, and then I'm going to put it next to this equation. But really, it's just this equation. So you're going to literally implement this equation. So does that make sense? Okay, good. Okay, so in other words, we have now expressed the color of this ray as a weighted sum of colors along the ray with a fixed number of samples. And it turns out this thing is just also straightforwardly differentiable. You can convince yourself of this fact because, of course, all of the operations that we just discussed are differentiable. They're just sums and products. So you can literally code this up in PyTorch, and you don't have to do anything extra, and AutoGrad will just take care of the rest. Okay, so differentiable renderer is done. So we now can pick a representation of our, this is what we talked about in the past 2 lectures. We can pick a representation of our 3D scene. We can pick one of the differentiable renderers that we just discussed, and then we just code up the differential renderer, and then we just optimize it. Oh, sorry. Okay, cool. Let's do a little test case. So this is actually, this was a paper that I wrote in 2019. It was called Scene Representation Networks. Scene Representation Networks had a neural field for the 3D scene, and it had the sphere tracing-based renderer that we discussed earlier as the renderer. So we pick a differential renderer, which in that case was sphere tracing. We pick our scene representation as a neural network that maps a 3D coordinate to assigned distance and the color. Now we have a data set. Let's say we have lots of images of a single car. And now we can just implement this and hit it with a deep learning stick. What falls out? It looks like this. So I'm going to skip through this one more time. So we randomly initialize the weights of the neural network. And now what you see here, it started out as this red color, right? It was just randomly initialized. It was just red. And then as we were optimizing, it slowly converges to the images of the underlying car. I'm going to play it one more time. So here you can literally see the optimization. So it starts with the random initialization, which is just red. And then over iterations, you can see it converge to each of the different observations of the toy car, correct? This is what it looks like. And then afterwards, you can use this thing now to move the camera to any arbitrary 3D location. And then you just use the same rendering algorithm that you just used for optimizing it. And then you can render it from every point in space. And this is what you're seeing here. So here now we're just moving the camera around the car that we just fit. And this car is now literally encoded in the weights of a neural network. So you have a neural network that mapped every 3D point to assigned distance and to a color. And now you have encoded this car in the weights of this little neural network. I thought that was really cool. And what I'm showing here is, by the way, the normal map. So I'm just like, just to be clear, when you do sphere tracing, right, at the end you get the estimate of where your surface lies, because that's the final iteration, right? And that basically, you can use that to directly estimate the depth, right? You can say, okay, what is the distance of the camera to the point where my sphere tracing algorithm ended? That's the depth. And then, as we discussed, you can, from the depth map, compute the normal map, and that's what we're visualizing here. And you can basically see that the normal, yes? I erased it. That comes from the sphere tracing algorithm stopping at stopping in the middle of space, basically. The sphere tracing algorithm stops in the middle of space, and what you can imagine is that the point where it stops is still related to the assigned distance, and the assigned distance basically, yeah. Does that kind of make sense? Yeah. Yes. Yeah, in this case, actually, the mesh would look kind of like the normal map, so it would look reasonable, but yeah, it wouldn't be amazing. Yeah, this is actually a big problem with all of these things. It's like getting the. Yeah, cool. So, so that was what I did in 2019, and then 2020 happened, and there was this paper called NERF, and NERF. So, did I not have one more thing? Yeah. And since then, this whole field blew up, which is why we have this lecture today, and which is why I'm a professor here. But basically, this whole field blew up, which is that since we basically started building these differential renderers, and then what did that really open up? It opened up the way of doing 3D computer vision, of reconstructing 3D scenes, even though we only have images of 3D scenes, which really is the way in which the world works, because the way we measure 3D scenes is by running around with a video camera. That's the thing we have. We only ever have images. And even as you know, the camera poses are kind of a pain to get because you have to run CallMap. But we glance over that fact for now. But actually, images in camera poses are relatively easy to get. The 3D scenes are really not easy to get. And it's particularly not easy to train neural networks to predict 3D scenes. But now we have developed the toolset. And this has spawned this whole thing. So NeRF has by now 3,500 citations over 3 years, because lots of people have built on it. So lots of stuff happened. And now we have everything in place to basically build a little, I'm now going to walk you through, this is, I hope, going to be somewhat cathartic. I'm now going to show you a bunch of papers that you can just slot together from all the pieces that we've learned so far. Okay? So one piece is going to be the parameterization of the 3D function. And we talked about a few different ones. We talked about voxel grids, about neural fields. We talked about these hybrid representations. That's one piece. Another piece is basically the model for the geometry and the appearance of the scene. We talked about sine distance functions. We talked about density functions. We talked about occupancy functions. That was another thing, right? Then the forward map is basically the differentiable renderer. We talked about sphere tracing. We talked about volume rendering. There are a few more. And the inference we don't talk about for now. Okay, so here's a paper that I wrote in 2018. This was my first paper in this whole field. So in 2018, I wrote this paper called Deep Voxels. I picked a voxel, as the name suggests. I parameterized the 3D scene as a voxel grid. And then I implemented what you can imagine a self-rolled version of volume rendering, because as I had mentioned, I didn't know what volume rendering was, and no one told me. So I instead was like, okay, well, intuitively, I'm going to shoot a ray, and then I'm going to compute the color of the ray as the weighted sum of colors that are stored in the voxel grid. And the way I'm going to compute the weights for that is via softmax. So I said I stored features in the ray, I sampled points along the ray. For each point, I would get a weight, and then I would do a softmax weighted sum of the colors along the ray. And that's what I mean. Like volume rendering, it would have helped to know about volume rendering, because then I could have done a better job at it, but I didn't, and it's still fine, right? You can just roll something yourself, it still kind of works. So what you see here is actually renderings from that scene representation. So these are novel views. This is a thing at Stanford that we captured with our little camera. And then and this other thing is in the Technical University of Munich. And then we captured that, and we ran our algorithm, we fit a voxel grid, and then we can render novel views of the 3D scene from that. That's pretty cool. Then scene representation networks we actually already discussed. So then I was like, okay, voxel grids suck because they scale cubically with the spatial resolution. And then neural fields were the new thing. And I was like, neural fields, magic. We store the scene in the weights of a neural network. Fantastic. That sounds way cooler. So I picked that as the scene representation. Then I parameterized the scene as a sine distance plus a color. And then we built a sphere tracing algorithm to render the thing. And then this is what you can get from scene representation networks. So this is actually a scene that I ran much later. This is actually a baseline. Scene representation networks was one of the baselines for NeRF, and this is actually taken from the NeRF paper. So they ran scene representation networks on their own data set that they had captured. So I didn't capture the scene. This is part of the NeRF data set, but they ran scene representation networks on that. And definitely not photorealistic. Looks okay, but like clearly signs of life, like some 3D geometry. And actually, the point that I was interested in back then, which is what we're going to discuss in the next few lectures, is generalization. The key part of scene representation networks was reconstructing a 3D scene from a single image, not from 100 images. But we're going to talk about that later. Okay, so these were some renderings you can get out of scene representation networks. Okay, and then NeRF happened. NeRF was, now you know each of these pieces. NeRF parameterizes the scene as a neural network, as a neural field. So it's a neural field that maps a 3D scene to a color and a density. So we're taking this volume rendering approach. We're modeling the scene as a color and a density at a 3D point. The forward map is exactly volume rendering, what we just discussed. Actually, the slides that I used to explain it are from Ben Mildenhall, who's the first author of NeRF. He kindly gave them to me. And then the inference model is just, you have hundreds of images of a single scene, and you're just fitting your 3D representation to the thing. And this now, do I not? Okay. So this now is starting to look photorealistic. So these are renderings of a 3D scene that is reconstructed using NeRF. And so this almost gets us to photorealism. Yeah, so pretty cool. So this what you see here on the right is the depth map. So this is, we should have mentioned, how do you think can you get the depth of every ray? Like remember that you have this transmittance, right, which is the probability that a ray stops at that location, and we express the color of the ray as the weighted sum of colors according to these weights. What? Yeah. Thresholding. Yeah, you could threshold the transmittance. Yeah, yeah, yeah. Good idea. You could do that. Another way of doing it is you can say, we're going to take the weighted sums of depths. Like you're going to take the right, because you can use the expected value of the color, or you can just compute the expected value of the t itself, and then you get the depth map. So this is what you see on that. But you're right, you can also use different statistics. So instead of the expected value, you can use the mode. And there's actually papers that visualize the mode instead of the mean or like the expected value. Okay, good. So let's talk about a few problems with this. So actually, one of them you should already know. We discussed about these field parameterizations. So in this case, the neural network is parameterized as a just neural the 3D representation is a neural network. What does that mean? For each, like this scene here is rendered with I think like 200 samples per ray. So for each pixel, you have to sample 200 points along each ray. Does that make sense? And now the problem here is that for each of these samples, you have to do a forward pass through a neural network. And the neural network is pretty beefy. So this is really expensive, like really expensive. Like rendering one of these images is like, at this resolution is probably like 25 gigabytes of GPU memory, just rendering the image. And then if you compute the gradients, it's probably like, it's twice that, right? So it's going to be 50 gigabytes. If you want to do a forward pass, if you want to render a single image, it would be extremely expensive. So how can you train it in practice? The way you train it in practice is you render single rays during training time. So instead of rendering the whole image, you'll just subsample a few pixels for each image, and then you just evaluate only these few pixels. So then you can optimize it even though the whole image doesn't fit into the GPU. Does that make sense? Okay, so that's really bad. So it's super slow to render. It's super high in memory cost. But as we discussed, the benefit of neural fields is, of course, that the final representation is really small because it's the weights of a neural network. Versus if you imagine the voxel grid that would store this level of detail, imagine what the side length of the voxel grid would have to be. It would have to be really small. So this is an upside. And then the other point is that the geometry that you get out of this, I mean, here, these depth maps are really fantastic, but in general, the geometry that you get isn't quite that good. It's going to be like cloudy, and the surfaces aren't exactly smooth and stuff like that. And the problem is it requires like lots of images. For this to work, it requires like hundreds of images. So even for this simple scene, it's probably like on the order of 100 images. Yes? Yeah. Yeah. You could just re-render. You could just send them weights. Yeah. No, the weights are actually really cheap. It's like it's like a few million floats. This thing here in particular is a neural network with width 512 and 8 layers. So it's 512 squared times 8. That's the number of parameters. Someone who's better at math than me, give it a shot. 250,000. Is that right? Or 2.5 million per layer. Yeah. Anyways, I'm not going to embarrass myself, but it's not that big. It's much smaller than the equivalent voxel grid. So this is really great. So this is actually really, this was like a huge boom. Like people were like, holy shit. So actually at CVPR, still today, like I'd say a solid 10% of the papers are papers that build on top of NeRF. Because right now it's still very hot, although it's dying down now. Okay, so NeRF, really cool. And now I hope that now we're going to do some questions. So if you wanted to make it faster, like if you wanted to make the rendering faster, any ideas on how to do that? Yes?
You can make the MLP smaller.
Right, you can make the MLP smaller, good point, right? Because now if the MLP is smaller, like a single forward pass will take less time and it's going to be less memory cost, makes sense? But if you make the MLP smaller, unfortunately also the quality gets worse. Because remember, there's actually one part we skipped, like this uses positional encoding, so it's not just an MLP, it also uses these positional encodings that we discussed, sine, cosine embeddings. And okay, but yes, you could make the MLP smaller. Any other ideas? Maybe something that doesn't make the quality worse? We talked about, yes? Something we talked about over the past few lectures? Yes? Yeah, so instead of having a 3D, instead of only having a neural network, why don't we, for instance, you could use a voxel grid instead of a neural network. The voxel grid is really fast to sample, right? Like it's in fact it's basically free. Sampling the voxel grid is like a lookup in an array. It's like basically free. So you could parameterize the scene as a voxel grid. But now, of course, again, there's this like quality trade-off. Now the side length of the voxel grid would have to be pretty high. Okay, so that sucks. Or you can do the stuff which is these hybrid representations which we discussed. So you basically have your voxel grid, and the voxel grid stores features in every voxel. And now when you sample a 3D coordinate, you interpolate the features at the 8 corners, and you give it to a neural network, a small neural network, and then the neural network basically does a little bit of interpolation. And it turns out that that got us really far. So here's a set of papers. In 2022, there was Planoxels. Planoxels parameterizes the scene as a voxel grid. And that was the first, they were like, okay, you don't need the neural network. We're just going to use it as a voxel. We're going to just use a voxel grid. And it looked pretty good, but it wasn't quite as good as the neural field. And there's another paper that was concurrent, which is called direct voxel grid optimization. And then the image that I showed you the video that I showed you at the beginning of the lecture, this scene here, that is actually from NVIDIA. And what did they use as a scene representation? They used a set of voxel grids, multi-scale voxel grids, and then they had finally a hash grid. We discussed this in 2 lectures ago. So for every 3D point, you'll first sample like a set of voxel grids with different spatial resolutions. And the moment that you can't have like super high resolution voxel grids, so at some point you're going to switch to a hash grid. So you're going to take the 3D coordinate, you're going to hash it, and the hash just stores a bunch of neural network features as well. And then you just concatenate all of that and stick that into a small MLP. And then that gave you the quality that we saw there. Then you could, of course, do something like there was a paper that did it with point clouds. So you take the COMAP that you take the point cloud that pops out of COMAP, which is, as we know, not that dense, right? So it's like not good enough for rendering itself. But now at every point, you're going to store a little feature. And when you shoot a ray, at every point along the ray, you're going to interpolate the features that are stored in the point cloud, and you're going to give those to a neural network. And then you can do it with the point cloud. And then there was this paper called EG3D or TensorRF. And what these did is they parameterized the scene as these triplane representations, which we briefly mentioned, right? So you can also say, well, we're going to have 3 planes floating in space, like one plane like that, which is a 2D grid, one plane like that, which is a 2D grid, one plane like that, which is a 2D grid. And now when we want to query a point, we're going to project it on all 3 grids. We're going to get the features that are stored at these positions. And now that we're going to give to a neural network. And that's going to give us the density and the color. And so that's a way of trading off the size of the neural network and the size of the representation, and it speeds it up a lot. Does that make sense? Great. Yes? Yeah, so Planoxels, Planoxels used volume rendering, like the proper one, not whatever I cooked up. That was one contribution. And then it also had a bunch of low-level CUDA code that made it faster. So these were mostly, so those were basically the 2 core contributions. So deep voxels I wrote at a stage where I still thought that any of this had anything to do with machine learning, which it doesn't. All of the stuff that we're discussing right now is you solving a little optimization problem. This has nothing to do with AI. There's no learning in here. Even though we're using differentiable programming to fit these things, nothing has anything to do with machine learning. Okay. Okay, we're going to skip this because otherwise we're not going to, okay, whatever. Okay, yeah, actually, I think this is almost the end. So two more things. So one thing that is noteworthy is we talked about the rendering equation. So what we are doing right now is we're approximating the rendering equation in a really funky way, which is we're saying that instead of having light, like you can notice this, right? We're not actually tracing any rays here. We're not actually having light bounce around in the scene. Instead, what we're actually doing right now in all of these rendering algorithms, we're saying that every 3D point in space emits light. So actually, it is as if every surface in the scene would be emitting light, and then we are forgetting about light bouncing around. We're just saying every surface is emitting light, and so we only have to find the surface, and then that's it. So actually, what we're doing is we're throwing everything away except for we're saying every surface now emits light. And in the thing that we discussed so far, every surface only emits light equally in all directions, right? Because you sample a point, and at that point, you have a color, or like a radiance. So no matter from which direction you look at that point, it's always the same. So right now, we're modeling the radiance as being viewpoint independent. But this is actually easily fixable. How can you fix it? You can, of course, make the color viewpoint dependent if you want. So instead of imagine, again, you model it as a neural network, you can sample a 3D coordinate, and it gives you a color. But you can also give the neural network as an additional input the view direction. You can say, okay, give me the color dependent on the 3D position and the view direction. Or in the voxel grid, you can say you have voxels, and then at every voxel, you're going to store basically a little view-dependent function. Okay, and what that buys us is it allows you to do, this is actually what NeRF also introduced. So NeRF said, okay, we're going to make the color view dependent. And now if you have enough images, you need a lot of images, then every 3D point can now have several colors. And this is what allows you to do this. So note that for all of these reflections, really the same 3D point in space has different colors depending on how you look at it. And that's why you need to make the color view dependent. It is noteworthy that this has nothing to do with the physics, right? This thing doesn't actually model the reflection. It doesn't know about the reflection. It doesn't know anything about materials. It doesn't know about anything about that. It's just saying, oh, I'm just going to explain the images by a viewpoint-dependent function. Okay, and here's a little bit of food for thought. So we discussed all of these renderers that work like this. So volume rendering, sphere tracing. Here's a little food for thought. Why are we doing all of this? Couldn't we just have a function that doesn't take as input the 3D points along the ray? Instead, it just takes as input the ray directly. And it just gives us the color of that ray. Right? Wouldn't that be neat? And you can think about, you can do that. Whatever, we're going to discuss this in the next lecture. Like, let's just remember that. It looks, if you try to fit it to a scene from these input images, it looks like that when you try to render novel views. And you can think about why it looks like that. And maybe keep that in mind. We'll get back to it eventually. And that's it for today. Let's wrap it up. Cool. Thanks for coming.